Relaxation method. Relaxation method is an indirect method to solve the system of linear equations. Let's see how this method can be used to solve the given system of equations. Okay, now this is a question. We have three equations in the system. First, we have to check whether the system is diagonally dominant. To check that the system is diagonally dominant, we have to write the coefficient matrix. Once you have written the coefficient matrix, check that the diagonal elements are dominant in each row. That means in the first row, the diagonal element is 8. 8 should be greater than the sum of the modulo of the other two numbers. Here it follows the diagonal dominance, and looking at the second and third row also, we can see that the diagonal element is the dominant one. So we can write that the system is diagonally dominant. The given system is diagonally dominant. If it is diagonally dominant, then by relaxation method, it quickly converges to the solution. We'll get a solution quickly. Okay, the first step in relaxation method is we have to find the residuals. Okay, so from the given system of equations, the residuals for each equation in the system should be written. So that we can write as a relation like let R1, R2 and R3 be the residuals for each of the linear equations. So we assume that R1 is a residual for the first equation. It can be written as R1 is equal to 8x plus y plus z minus 8. That is, either you put this constant, move this constant to the left side, or move these three variables to the right side. Any way you can do, but you have to write the residuals by on one side the residual variable should be represented, and on the other side all the other values should be given. So from the first equation, the residuals are written as R1 is equal to taking all the values to one side. So here I have moved the constant to the left side. So I will get an equation 8x plus y plus z minus 8 equal to R1, which is written in this manner. Okay, so R1 is equal to 8x plus y plus z minus 8. Now in the second equation, see, while moving 4 to the left side, I will get 2x plus 4y plus z minus 4 is equal to R2, which is written as R2 equal to 2x plus 4y plus z minus 4. Like this way, the third equation can also be written as x plus 3y plus 5z minus 5 equal to R3, which is written as R3 equal to x plus 3y plus 5z minus 5, and mark this system, the residual system, as equation. Now our aim is to find the values of x, y and z for which these residuals will be 0. That is, we have to find the values of x, y, z such that the residuals R1, R2, R3 will be 0. If we get such a value, that means those are the exact values of x, y and z. But in all cases, we will not be able to get such a value, that is, for which the residuals are 0. So we liquidate the residuals R1, R2, R3 by taking better approximate values of x, y, z. That is, we try to get a value which is very close to 0 for the residuals. That is what we are going to do here. For that, we need two tables. One is an operation table and another is a procedure table. The operation table, first we have to write the operation table, which with the help of this operation table we will be writing the procedure table or the relaxation table, from which we will get the values for x, y, z for approximate values, or by approximately converting the residuals to 0, or sometimes in some cases we may get 0 residuals also. Okay, now the operation table. So the operation, this is the operation table which we are going to write now. Let's look how we have written this operation table. Okay, in the operation table, this records the changes in the values of the residuals for unit changes in x, y, z. Okay, the operation table gives the details of the changes or the increment in the values of the residuals for unit change in values x, y, z. Okay, so then let's look at the first row. In the first row we can see that the value of x is 1 and y and z are kept as are given as 0. That means the first row shows us that for a unit change in x, keeping y and z as constant, the changes in the residuals are like this. That is, for a unit change in x, keeping y and z as constant, R1 changes by 8 units, R2 changes by 2 units, and R3 changes by 1 unit. That means for a unit change in x, keeping the others constant, the maximum change in the residual is for R1. Okay, so like that, in the second row, look at the second row. In the second row, it's shown that for a unit change in y, what are the changes in the residuals? So for a unit change in y, keeping the others constant, you can see that R1 changes by 1 unit, R2 by 4, and R3 by 3. That means for a unit change in y, the maximum change is for R2. In the third row shows that keeping x and y constant, we are changing 1 unit for z. So for 1 unit change in z, keeping the others constant, the changes for R1, R2 and R3 are given, in which the maximum change is for R3. So using the first row, the maximum change will be for R1. The second row, in the second row, the maximum change will be for R2, and in the third row, the maximum change will be for R3. Now, how to write this table? First, you have to specify the operations. That is, you have to just label the rows so that we will be able to refer these rows using these labels. Okay, just for reference, we are labeling it. And now, here, in the we have written all the unknowns which are in the given system plus the residuals. How many equations are there? We have 3 equations, so there will be 3 residuals. Okay, so the residuals are the x, y, z, and the residuals are the headings which are given here. And in the x, y, z case, over here we have written the unit matrix, right? The unit matrix is written here. And in the residual portion, look at the values. Here the values are 8, 2, 1, which is obtained from the equations 8, 2, 1. Then the next one is 1, 4, 3, which is 1, 4, 3. And the last one 1, 1, 5, which is 1, 1, 5. That means the matrix A, the coefficient matrix A, after converting it into transpose, we have written it here. That is, A transpose is taken here. So for simplicity, I'll write in the XYZ portion, we'll be writing the unit matrix, and in the residual portion, we'll be writing A transpose. You can see that this is the matrix A, and the transpose of matrix will be interchanging the rows and columns. Here the first row is 8, 1, 1. In the transpose of A, this first row will become the first column. Look. First row has become the first column. In the second row will become the second column, and the third row will become the third column. This is how transpose is taken. So the operation table is constructed by writing the unit matrix and the transpose of the coefficient matrix. This is how we write the operation table. Okay. Now we'll go to the relaxation table. Here we are actually the operations are performed here to find the values of x, y, z. The headings are same as the operation table. We have x, y, z, r1, r2 and r3, and a side for operation to specify what operation we have done here. Okay. Now the relaxation table or the procedures table start with 0 values for x, y and z. So we start with putting 0 values for x, y and z. So in equation 1, by substituting 0 for x, y and z, we will get the values for the residuals, and that will be substituted in the residual part of the first operation. That is, we will continue the numbering from the operation table. So there we had 3 rows, so L1, L2 and L3 is already given, and in the relaxation table we will start with L4. So L4 is obtained by substituting x, y, z as 0 in equation 1, where you get the residuals, the values for the residuals, and that will be substituted here. Okay, this is the starting step for the procedure table or the relaxation table. Now we have to choose a residual from these three. That is, at a time we will be reducing only one residual. Okay, our aim is to make the residual values 0. Okay, so at a time we will be choosing one residual. For that we will choose the highest number. That is, after taking modulo, we will take the highest value. So ignore the signs of the numbers and choose the highest value. So here we have -8, -4 and -5. Ignoring the signs, we will get 8, 4 and 5. In that, the highest value is for 8. So we will first reduce the value 8. So 8 is for R1, right? So R1 is to be reduced, and we are actually trying to make it 0. So we have to find an equation which will make this R1 0. Okay, so we have -8 here, and if looking at the operation table, we have to choose a row from the operation table which will reduce R1 maximum. Okay, so we know that in the first row, for a unit change in x, R1 is reduced to the maximum, and in the second row R2 will be reduced to the maximum, and in the third row R3 will be reduced. Okay, so here, since in the procedure table we have chosen the highest value and it is for R1, we know that from the operation table, in the first row only R1 will be maximum reduced. So we will be writing a row operation based on that row, that is based on the row L1. Okay, and the equation will be written as we have to give the next number for this operation. That is, after L4 we will be writing L5 is equal to L4. Since we have -8 here and 8 here, even if we simply add these two numbers, it will be reduced to 0. So the operation is L4 plus L1. So L4 plus L1 means -8 plus 8 will give us 0. So this should be done to all the residuals. Okay, so then we have got the equation L5 equal to L4 plus L1, and then using this equation, only the residual part will be changed. And in the XYZ portion, what we have to write is the change which we have made in XYZ. So by choosing the operation L1, it is clear that we have used 1 unit of x, keeping y and z as constant. Only then we can choose 8 from R1. So in the XYZ portion, just write the change. So if we have just multiplied 8 by 1 to give us 8 itself, because we need 8 completely. So we have just the changes 100 is the change what we have to record here. So 100 will be written as such, and in the residual part the operation L4 plus L1 will be performed. So L4 plus L1 will give us -8 plus 8, 0. In the R2 case, -4 plus 2 will give us -2. -5 plus 1 will give us -4. Okay. Now in this portion we have to choose the highest number, ignoring the sign. So we will get 4. So next we are going to reduce R3. 4 is for R3. So reduce R3 with respect to the operation table. So we have to look which in the operation table which row will maximum reduce R3. So R3 we have already seen that in the operation table row 3 R3 will be reduced to the maximum. So using L3 we will be writing the row operation. Now look at the numbers. In L3 R3 value is 5 and in L5 R3 value is minus 4. So if we simply add L3 and L5 we will get 5 minus 4 equal to 1. That itself reduces the number from 4 to 1. Okay, so that is enough. So that means we are using 1 unit completely to reduce R3 right now. So let's write the equation. L6 becomes L5 plus L3 and the changes are recorded. The change is set keeping x and y constant and changing Z by 1 unit. We are going to find the effect in residuals. So the equation is L5 plus L3. So L5 is 0. 0 plus 1 will give you 1. Then minus 2 plus 1 will give you minus 1. Minus 4 plus 5 will give you 1. Here I can choose any residual as all the values are 1 after ignoring the sign. I have chosen the first one, that is R1. So to write a row equation for R1, to reduce R1 to 0, I have to choose the first row, that is L1 in the operation table. Right. Now look at the numbers. Here I have 8 in R1 and 1 is to be reduced with respect to this 8. But you can see that 8 is too large for 1 to be reduced to 0. Right. So I have to convert this 8 to a number which will reduce 1 to 0. So to reduce 1 to 0 I need minus 1. So minus 1 can be obtained by multiplying this 8 into minus 1 and then dividing it by 8. Okay. By multiplying minus 1 to 8 and dividing it by 8. Then you can see that I will get minus 1. So that means I have to multiply minus 1 by 8 to 8. Okay. So that is what is going to be written in the equation. Okay. So that the meaning is that in this case, that is to reduce 1 to 0, I don't need 1 unit change in x. I just need minus 1 by 8 units. Okay. So the equation becomes L7 equal to L6 plus minus 1 by 8 into L1. That means instead of 1 unit change in x, I have made minus 1 by 8. Minus 1 by 8 is minus 0.125. So minus 0.125 change in x, keeping y and z as constant. Let's see what other values of residuals. So in the residual part, this equation is to be applied, and after applying this equation we will get the values as this. 1 will be reduced to 0 and R2 minus 1 minus 0.125 into 2 will give you minus 1.25. Like that R3 is also obtained. Okay. Now in L7 choose the highest number ignoring the sign of the residuals. So you can see that R2 gives the highest number, that is 1.25. Now we will be writing the equation to reduce R2 to 0. So to write the equation, so we have to reduce R2 with respect to the row operation L2. In L2 you can see that the value of R2 is 4. So here also we don't need 1 unit change. So we just need 1.25 divided by 4 units. Okay. So we find the value which should be multiplied to L2 by just dividing the number. That is 1.25 will be divided by 4 in this case. And look at the sign here. If we have minus here, then we will be using a positive number here in the equation. Only then we will get a 0 value. Okay. So in this case the L8 will become L7 plus 1.25 divided by 4 into L2. And record the change here and find the residuals using the equation. Okay, now we'll check one more. In L8 you can see the highest number is 1.8125, which is for R3. That means in the operation table we will be choosing L3 and the value of L3 is 5, right? So the equation will become, we have to multiply L3 by 1.8125 divided by 5, and the sign will be, since we have positive here, the sign in the equation will be negative. That is L9 is equal to L8 plus minus 1.8125 divided by 5 into L3. Record the change. While recording, you have to write the sign also. Then find the residual values using the row operation. So these are the values which we will get, and we have to stop when the residual values, you can see that either you should get all 0 values for residuals, but it is not possible for all the problems. So we will stop when we get a value close to 0, that is 0.00 or 0.000 values. Okay, so here I have stopped at 0.00 values. So look at the last row, you can see that in L13 the residuals are minus 0.0083 and minus 0.008 and 0. So I have stopped here, and the solution is obtained by adding the values in the corresponding variables. Okay, the x value will be obtained by adding the values in this column, the y value will be obtained by adding the values in this column, and z will be obtained by adding these values. So after adding the values, I have got the solution as x equal to 0.875, y equal to 0.4168 and z equal to 0.5749. So these are the values of the variables, and the residuals will be R1, R2 and R3. That is, the solution of the given problem is x equal to 0.875, y equal to 0.4168, z equal to 0.5749, and the residual values are the values that we obtained in the last row. That is R1 equal to minus 0.0083, R2 equal to 0.008 and R3 equal to 0. So you can check the values by substituting these values in equation 1. That is, by substituting the values of x, y, z in equation 1, you will get the same values, that is 0.0083 minus 0.0083 for R1 and 0.008 and minus 0.008 for R2 and 0 for R3. So after substituting, that is substituting the values of x, y, z in the first equation, we will get the value this, which is same as the R1 which we obtained in the procedure table. Like this you will get the rest of the values. So in this way you can check whether the values you got is correct or not. So this is the solution for x, y, z for the given system of equations using relaxation method.